Hi, everyone, and welcome to the session, How to Build Secure Connected Consumer Products and Solutions. My name is David Walters. I'm a Senior Partner Solutions Architect at AWS. My role is to work with our IoT hardware partners to build solutions on AWS IoT using AWS's Edge solution and cloud services. As you can imagine, IoT security is a topic that permeates through every interaction I have with partners, and it is a subject that I'm passionate about. First, let's look at what customers are doing on AWS IoT. Customers are building innovative products and solutions in home automation, home and commercial security, networking, energy management, and health and wellness, just to name a few. There are many challenges to building connected products. First, no one builds a connected product just for fun. Customers need ways not just to collect data, but to turn that into business outcomes and value, such as new revenue streams. Managing and scaling large fleets of devices is a challenge. It's one thing to build a single device and put it somewhere in a controlled lab environment, but it's much harder to scale to millions of devices and understand what's happening across your entire fleet of devices throughout their lifecycle. Of course, security is everyone's priority. Security of our customers' data, security of our intellectual property. We need a way to secure our connected products from individual devices to our scalable cloud infrastructure. And finally, we want customers to be delighted with their experience using our products. If there are issues, we want to resolve them in a timely and efficient way. And ideally, we want to automate as much of this process as possible so that we can focus on the things that matter most to customers. Today, we're going to focus on my two favorite topics: managing and scaling large fleets while maintaining security from device to cloud. What are we going to cover today? Today, we're going to cover foundations of IoT security. We're going to cover secure manufacturing and provisioning of IoT devices at scale and device security best practices. We're going to cover onboarding and managing a fleet of devices and monitoring security vulnerabilities in the cloud throughout the entire device's lifecycle. We're going to look at how to automate mitigation actions from security threats. And we're also going to look at how you update your fleet of devices over the air. First of all, let's ask, what is IoT security? There's no such thing as secure or insecure. Every security-related decision is a trade-off between convenience, cost, and level of security. We can roughly separate out IoT security concerns into a few categories: identity and provisioning, onboarding and authorization, management, auditing and monitoring of our device behavior, alert and automatic mitigation actions, and finally, patches and updates over the air. Managing IoT security in the cloud presents an opportunity to increase your security posture. AWS IoT offers features, services, and tools across each one of these categories to help you manage and secure your connected products at scale. Identity is the foundation for IoT security. Every device needs a unique identity that is protected because identity adds context to the data that we collect. For example, you have millions of devices connected, producing tons of data, and we need to understand from each data point where that piece of data actually came from. Identity allows us to manage our devices as we scale. And such identity is a foundation also for AWS IoT security. We typically do this with public key infrastructure, or PKI for short, with X509 certificates. What does this actually look like in practice? We need to establish a chain of trust. We're going to start in the middle of this diagram and look at a device. A device comes out of the manufacturing scenario with a private key and an asymmetrical public key. The first thing it's going to do is generate a CSR, certificate signing request, to a signing certificate authority. That signing certificate authority is going to check if it trusts that device. And if yes, it's going to issue and sign a certificate to that device. Once that process happens, the device now has a private key, a public key, and an X509 certificate that becomes the device's unique identity. Finally, the device is going to try to connect into AWS IoT Core using Transport Layer Security, or TLS 1.2. On AWS IoT Core, you're going to have a copy of the public certificate registered on IoT Core, as well as in some cases, a copy of the certificate authority. When the device connects using TLS 1.2 and mutual authentication, AWS IoT Core will be able to verify that device's identity. This process happens both ways because AWS IoT Core will also send its server certificate to the device and say, hey, I am a genuine AWS IoT Core endpoint. The device is going to verify that server certificate. And once that process happens, the device is securely connected into IoT Core with a chain of trust established. Now, it's easy to do this with one device, but it's a lot harder when you have a supply chain, when you're building millions of devices to go into distribution to send to your customers. You typically have a connected product supply chain that would look like this. Starting from the left of the diagram, we have the supply chain. The supply chain are vendors that create the different components that go on your connected product device, like a processor, the PCB, the parts, and the housing that your device goes into. Typically, those components are sent to a contract manufacturer who is responsible for assembling those and actually building the products as they look like going out to the customer. The contract manufacturer is also responsible for programming the device with firmware that you, as the device maker, the OEM, have provided to the contract manufacturer. The firmware is your OEM, that's your specific intellectual property that is being programmed into each individual device. Products go into distribution, which they're typically sold on to end customers. Somewhere in the middle there, you've also got the AWS cloud account that is owned by the device maker. Customers need ways to register and connect their devices using something like a mobile application. And you as a device maker need the ability to manage and update your devices over the air. Which part of this connected product supply chain do you actually trust? Well, the answer can vary. So we do offer some best practices for different areas in the supply chain and where you might actually trust your PKI and provisioning of devices' identity. First, let's look at identity provisioning by the OEM. In this scenario, OEMs maintain the most control of the provisioning process and the most visibility. They maintain complete control of their own public key infrastructure, like the signing certificate authority. It's their responsibility to load unique certificates and private keys, so the device's identity information, into individual firmware. And then they give that firmware to the contract manufacturer, who is responsible to then program each individual chip with each individual firmware. This is highly secure, and the OEM will maintain the most control of the provisioning process, but it does add significant complexity to the contract manufacturing process. It can add time on the production line, which does lead to increased costs to the OEM. Sometimes contract manufacturers have the ability to do this for you. So as an OEM, you might provide a single golden image or single standard firmware to load into each chip, and you give that to the contract manufacturer. The contract manufacturer can then interface with the device to produce the certificate signing request and load the unique certificates and private keys at manufacturing time. Contract manufacturer in this scenario has to be trusted because this is a significant area where your public key infrastructure could be leaked. So provisioning has to be done in a secure environment, and not all contract manufacturers have the capability to do this. For those scenarios, we do offer a third scenario, which is identity provisioning by an HSM vendor. An HSM is a hardware security module, which is an isolated processing unit for secure storage and to perform cryptographic operations. HSMs can be provisioned in secure infrastructure by the HSM vendor. So they typically have a common criteria certified secure infrastructure where they can actually generate the certificates and the private keys in a secure environment. And then they provide the secure elements already pre-provisioned to the contract manufacturer. In this scenario, your PKI is never exposed to your contract manufacturer, And your devices come from manufacturing pre-provisioned with unique identities. But of course, there's always a trade-off with cost, because when you add a hardware security module to a device, it does incur additional costs. AWS works with hardware partners in our AWS Partner Network to provide this ability to provision devices into secure elements. So 2 examples I have today are from NXP. NXP offers the EdgeLock SE050 secure element, or hardware security module, combined with a service they call EdgeLock to Go to help you securely connect your devices into AWS IoT Core. Infineon is another hardware partner that we work with, and they have the Optiga Trust line, which are secure elements that provide tamper-resistant protection of credentials that are provisioned securely in their environment. They also provide a trusted platform module called the Optiga SLX 9670 that provides secure storage of device credentials, as well as secure and measured boot so that your devices only run trusted applications. Keep that in mind, because we will cover what secure boot means shortly. If you're looking for qualified devices and qualified hardware from AWS partners, please take a look at the AWS Partner Device Catalog. The link is here below. You'll have access to the slides later, so you'll be able to go directly there and see devices that are qualified for free RTOS, for AWS IoT Greengrass. You'll also be able to see HSM vendors that AWS works with to provide this service. Now that your devices have been securely provisioned, either in an HSM or in the firmware or somewhere held on the device, we have to protect that device's security credentials. We have to prevent attackers from compromising our cloud connection by gaining access to those security credentials. We also want to protect the intellectual property. The intellectual property is the software, firmware, and hardware design that the OEM has invested into creating a connected product. We want to prevent attackers from loading unauthorized or malicious code. We want to prevent attackers from doing any physical tampering of the device itself. So let's look at a common design pattern to actually protect these. In order to protect your device's security credentials, we want to separate the credentials from the application. We want to hold those security credentials and the identity information in secure context. That secure context might be a hardware security module, as we've already discussed. It could be something like ARM Trust Zone or ARM Crypto Cell, or one-time programmable OTP memory. And also, silicon vendors sometimes provide proprietary secure storage solutions that provide a service that keeps those credentials secure as well. Your application will always run in an insecure context. So your application is connected to the internet and thus always has some level of threat exposed to it. But with APIs to the secure context, you can hold your security credentials in the secure context, and all of the cryptographic functions of the device can happen in the secure context. Thus, your security credentials are never exposed to the application. We also want to protect our intellectual property. So the most important point here is that you always want to sign your application firmware with a code signing certificate. This code signing certificate is different than the device's identity. You can think of the code signing certificate like the identity of the developer who created the application firmware. You can use a secure boot process to verify the device firmware signature at every level. And you also want to protect from physical tampering. So you might use inductive sensing or an open-close sensor to detect physical tampering of the device in every boot stage. So the way a secure boot process might look is that when you power on a device for the first time, it'll boot into the secure context, the first stage bootloader. This first stage bootloader should be immutable. It should not be changed ever in the device's lifecycle, and it should be an established root of trust that the device always knows, I know that this first stage bootloader has never been changed, and it cannot be accessed from an insecure context. First, it'll check the open-close sensor to see if the device has actually been opened up. If it has not been opened up, it is secure. The next thing it'll do is it'll take a hash of the application bootloader. It takes a hash of that application bootloader and does a checksum verification to ensure that this application bootloader has not been tampered with. If it hasn't, it'll transfer control to the insecure context. It'll transfer control to the application bootloader, which again, the first thing it'll do and check if the device has been opened. If the device is still closed, the next thing it'll do is take a hash of the application itself. It'll check the signature of the application against a code signing certificate that's held in secure storage, so that code signing certificate cannot be tampered with. If the application bootloader can confirm that the application has been signed with that code signing certificate, we know it is safe, and therefore we can transfer control to the application. If at any point the open-close sensor generates an interrupt to the application can stop working. This prevents an attacker from being able to see any data exchanged in the insecure context. Now that our devices are secure and we followed best device security practices, you need to be able to register them to AWS IoT Core so that IoT Core can establish the TLS mutual authentication when the devices connect. AWS IoT scales to billions of devices and trillions of messages. So we need ways to have secure, scalable registration and onboarding options for devices. Just a couple that we'll name today is just-in-time registration or provisioning, multi-account registration, and fleet provisioning. I don't have time today to cover all of these different options, but I will provide a link to a white paper that'll go more in depth into each individual registration process and when the scenario is appropriate. Today, I'm just going to focus on just-in-time registration in the context of consumer connected products. So first, let's look at a user's registration of a secure connected product. Starting from the left, we have a proud owner of a new connected product. So they've just purchased a new connected thermostat. The first thing they're going to do is they're going to go and download the thermostat OEM's mobile application. And they're going to register themselves as a user. This can be done on Amazon Cognito, which lets you add user sign up and sign in and access control to your mobile and web applications. After the user registers, an AWS Lambda function, which is a serverless compute service that lets you run code based on event triggers. Your AWS Lambda function will take the user ID of your newly registered user and input it into a database like Amazon DynamoDB. The next thing to do that the owner is going to do is they're going to register the device. That device might come with a QR code. What it's going to do is it's going to take the public certificate ID, or if you remember, the device's identity, and it's going to send it to an Amazon API gateway. Behind the API, there'll be another AWS Lambda function that's triggered that's going to input that device's identity into an Amazon Dynamo database. At the end of this process, you have a table in Amazon DynamoDB that has a user ID with an associated device or devices that the user has claimed. So let's look at this process from the device's perspective using just-in-time registration. Our connected product, a provisioned private key, public key, and certificate in it. The device is going to attempt a first connection with AWS IoT Core, and that connection is going to fail. But certain processes will happen in the back end that will allow the next time the device to connect to succeed. So AWS IoT Core is going to go check the signature of the device certificate that's sent up with the TLS mutual authentication handshake with the signing certificate authority. If it can verify that the signer CA has signed the device certificate, it's going to generate a lifecycle event on an MQTT topic. So AWS/events/certificates/registered/ the certificate ID of the signing certificate authority. We can use an IoT rule to trigger an AWS Lambda function. The Lambda function can go check the database to see if that device has been claimed. If no, we don't have to do anything. We don't have to register that device. If it has been claimed by a user, the Lambda function can create a certificate, or it can activate the certificate. It can create the IoT thing, and it can also create the IoT policy. Next time the connected product tries to connect into AWS IoT Core, AWS IoT Core knows its certificate, and it has an associated IoT policy with it, and so the device will succeed the second connection with AWS IoT Core, And now you have a connected product that is securely provisioned on AWS IoT Core. Let's talk about IoT policies and fine-grained access control. So each device requires an IoT policy that defines its allowed behavior. IoT policies can be set up automatically during the just-in-time registration process, like we saw on the previous slide. Devices that violate its IoT policy will be disconnected from AWS IoT Core. So if the device starts doing behaviors that it is not allowed to do, then it will just be disconnected from IoT Core. Because of that, we always want to follow the principle of least privilege. So we always want to make sure that the device is only allowed to do specific actions and nothing more. Let's look at an example IoT policy that follows the principle of least privilege. An IoT policy is just a JSON document that's attached to a certificate. In this specific scenario, the device is allowed to do 3 different actions. It's allowed to connect, it's allowed to publish, and it's allowed to subscribe. But it's only allowed to do these actions under specific scenarios. So the device is allowed to connect under a specific AWS region, in this case, US East 1, a specific AWS account ID, which is 1234567891012, and it's only allowed to connect with a client ID that matches its registered thing name. The device is allowed to publish only on specific topics. So it's allowed to publish on /home hub / it has to include its own thing name /THERM /temp. And it's also allowed to update its own device shadow. It's also allowed to only subscribe to device shadow updates. If the device tries to do anything outside of these defined actions, the device will be disconnected. Now that your devices are secure and they are registered with AWS IoT Core, you need to effectively manage them. You need a way to group and organize your devices logically with operationally focused groups, and you need visibility into your device's behavior throughout their entire lifecycle. You want to be able to monitor that device behavior for security threats or anomalous behavior, and you need a way to update your devices over the air to give your device new features, patch bugs, or even most importantly, mitigate any new detected security threats to your device. First, let's look at organization using the AWS IoT Device Management Service in the AWS IoT Core registry. First off, every device has a thing name. The thing name is the device's unique identity. So this has to be unique for your entire fleet of devices. So every device has a thing name that is unique. We also have thing types. Thing types are devices that share common attributes. So for example, you might have different types of connected products like a thermostat, a light bulb, and a door lock. And each of these different types of devices will have specific common attributes. Thing groups are logically grouped devices based on operational requirements. And so these are user defined, but in my example, I'm using location. So we'll look at an example of a geo-fenced IoT deployment in just a minute. And then finally, we have attributes, which are user-defined additional descriptors of the device. So the device might have common attribute types, and then each device will have unique attribute values. We can use fleet indexing to search our fleet to have visibility over specific devices that we want to see. So in this example here, on the bottom left, I have an example of a fleet indexing query. In this query, I'm looking for thing types of thermostat. I'm looking for all thermostats in Chicago because each thing group name is the name of a city. And I'm looking for thermostats that are running version 1.0. And I also want to see thermostats that are currently connected. So ones that have an active connection into AWS IoT Core. If I structure my fleet indexing query like this, I will pinpoint only those devices that meet that criteria. We want to monitor our device's behavior throughout its entire lifecycle. And AWS offers a service called AWS IoT Device Defender. Device Defender allows you to audit the security configuration of your entire fleet. It allows you to detect in real time anomalies in device behavior. And it gives you the ability to alert users and also support technicians, and also automatic mitigation actions to remediate any potential issues. You can audit your device fleet configuration based on time. So you might say, I want to run an audit and I want to report every 24 hours of my device fleet's configuration. Or you can do it on any on-demand event that you'd like by exercising the APIs. So with an audit, you can look at things like if there's a device certificate that's about to expire, you might want to know that so that you can rotate a certificate on a device. You might want to know if there's a device or multiple devices sharing a single device certificate and thus sharing an identity. You need to be able to mitigate that. You also would want to know if a CA certificate is going to expire soon, because any new devices that come online with an expired certificate authority won't be able to onboard with AWS IoT Core. It also looks at policies like AWS IoT policies to see if they're overly permissive. It also looks at logging. So you can have logging enabled or disabled, and you can also have different levels of log. And you'd want to know if somebody had disabled your logging so that you can investigate any further issues. And so every time an audit is run, you get a report sent to an email address of your choosing, or with a simple notification service notification. You also want to monitor the device's behavior throughout its entire lifecycle in real time. And so out of the box from the cloud, you can monitor things like connection attempts and disconnects. So if the device is frequently disconnecting, you might want to know about that. You might also define behavior for a device that says this device should only send messages of a certain size, let's say 1 kilobyte. If all of a sudden a device is sending 10 kilobyte messages to your AWS IoT Core message broker, that could indicate a compromised device. And so we would also want to know about that. By installing something called the Device Defender agent on the device, which is a piece of software, it can collect additional metrics like bytes in and bytes out from the actual device, establish TCP connections. So let's say it only needs one TCP connection into IoT Core, but now there are 3 or 4 open. That might indicate a problem. And finally, you can write your own custom metrics. And so you can extend that Device Defender agent to monitor specific things like CPU usage or battery charge level, process counts. And of course, you can get alarms and anomalies and notifications based on those custom metrics as well. Let's take a look at what that looks like in practice. Starting from the left-hand side of this diagram, we're looking at our connected thermostat. Normally, this device behavior is allowed a single TCP connection into AWS IoT Core. All of a sudden, we can see that an attacker has 3 additional TCP connections open on the device. The device will publish those metrics to AWS IoT Core, which will forward it into Device Defender. Device Defender will recognize that that behavior is anomalous for that thermostat. The first thing it's going to do is it's going to place the device into a quarantined thing group. That quarantined thing group might have a very restrictive policy because you don't want that device to be able to affect the rest of your infrastructure until you can verify that it is operating normally. It'll also trigger an Amazon Simple Notification Service. And Amazon Simple Notification Service can then generate an alert back to the owner of the smart product, and it can let them know that their device is unavailable for maintenance. Behind the scenes, you can automate your customer support workflow. So that SMS message might also trigger a Lambda function that kicks off your customer support workflow and notifies a customer support person to investigate the issue further. Once that person is done investigating the issue and indicates that the device is safe to remove out of quarantine, they can do that. And you can also notify the owner of the smart product and let them know that their device is back online. Finally, we need to be able to update our connected products. And we can do that with something called AWS IoT Jobs. With AWS IoT Jobs, we can organize and trigger over-the-air update campaigns based on groups of devices. We can monitor the state of that campaign for each individual device. We can see if it's a success or a failure as it executes. We can also target groups of devices, for example, using fleet indexing to update in bulk, or we can pinpoint single devices to update if we just want to update a single device. You can control the deployment velocity and set failure criteria to reduce the blast radius of any update. So what that means is you might choose to first update 5 devices in your fleet, and then 20, and then 100, and then 1,000. And you can monitor the progress of the campaign at each individual level to see if there's any issues. And before it goes out to your entire fleet of devices, you could stop that campaign if there were any issues, if you had a lot of failures, for example. And finally, and most important, you can digitally sign your job, and you can digitally sign the firmware that you send to your devices over the air before they're sent to the devices. Remember the code signing certificate that we spoke about earlier in the secure boot process. You can use that code signing certificate and the code signing service in AWS IoT jobs to digitally sign your firmware before they're sent to the device. So let's look at how an over-the-air update campaign looks like. In this diagram, we're going to start over here on the right from the device administrator. They want to update a batch of devices. And so the first thing they're going to do is create a job document. A job document is just a JSON file. In this JSON file down below, we can see it defines the actions that we want our device to do. And in this case, it's to download update.bin from an Amazon S3 bucket. So the device administrator is going to write a fleet index query for all of the targets that they're interested in updating, and they're going to start the campaign. AWS IoT Device Management is going to send an MQTT message using the MQTT broker from AWS IoT Core to notify each device that it's waiting for an over-the-air update. The device is going to go and update the progress, saying, okay, I've gotten the update, and it's going to go do the action, which is to download the update.bin from Amazon S3. After it downloads update.bin, it's going to verify the update authenticity using the code signing certificate. And finally, it's going to report back to the cloud, I've successfully updated myself, and I trust that the firmware image that I've received is valid. Your device administrator can monitor the progress of the OTA update campaign throughout its entire progress. Finally, that code signing certificate, while it's held in secure storage, the next time that device reboots, it can then again check the validity of that firmware image to ensure that it is authorized and valid before booting into. Now we've looked at how to build secure connected products and keep them secure for their entire lifecycle. AWS IoT supports your journey by providing services that help you manage millions of devices using reliable, persistent, and trusted communications. AWS IoT offers full edge-to-cloud security with dedicated services in the cloud to detect any security threats throughout the device's entire lifecycle, and gives you the ability to mitigate those issues in the cloud, over the air, down to your entire fleet of devices. Lastly, I'd like to highlight AWS IoT Device Software that AWS provides to help you build secure connected products and implements the best practices that I mentioned in this session. One of the services we offer is FreeRTOS. FreeRTOS is a real-time operating system, and we also include the connectivity and security libraries to implement best practices that we discussed today. It's free and open source under the MIT license, and it's widely distributed amongst silicon vendors and for over 18 years. It provides security libraries like PKCS11 to integrate with hardware security modules and secure elements. It implements trusted code signing so that it will only run trusted applications that have been signed with a code signing certificate. And we offer long-term support for 2 years, and it is CSIP Assurance Level 2 certified. For those that do not want to replace the operating system on their device, we also offer AWS IoT Device SDKs. They provide secure connectivity libraries for all classes of devices and operating systems in common languages. So you can easily connect your devices from any hardware into AWS IoT Core. It also provides deterministic performance with the AWS Common Runtime and a secure minified TLS stack called Amazon S2N, which can replace other TLS stacks like OpenSSL and other open source products. There are a lot of resources about AWS's approach to IoT security, so I've only highlighted a few of my favorite ones here. First of all, we have a white paper. So I mentioned earlier on in the session that there are a lot of different ways to scalably onboard your devices. And I mentioned just-in-time registration, and I gave an example of just one. We have a white paper called Device Manufacturing and Provisioning with X509 certificates in AWS IoT Core that covers all the different options and all the different ways that you can provision secure identity into devices. We have loads of blog posts. I just highlighted 3 of my favorites here. Please check them out, but also just search for IoT and security on the AWS blog, and you'll find loads of different articles that are really helpful. And of course, you can always learn more about the services that I mentioned today by clicking on the links below. And finally, always contact us for more information on connecting smart products so we can help you start that journey to building a secure, connected smart product. Thank you all for taking so much time out of your busy schedules to learn about IoT security. I'm available for the next few minutes to answer any questions you might have.